In a lab in Germany, scientists have just pulled off what once seemed like science fiction. They've teleported quantum information between photons emitted by two entirely different light sources, a milestone in the quest for a true quantum internet. Here's the challenge. In classical communication, we send bits across wires or fibers, but quantum information? You can't just copy it. Enter quantum teleportation, the process by which the state of a photon is transferred to another photon somewhere else without moving the original itself. Until now, one major roadblock. Both photons had to come from the same source or be nearly identical. But what if they came from two different sources, separated in space with differing properties? That's what this team tackled. Researchers at University of Stuttgart, together with partners, used two distinct semiconductor quantum dots, one producing a single photon, the other producing an entangled photon pair. Using clever quantum frequency converters, they tuned the mismatched photons so that they became indistinguishable, a crucial step. Then they performed a Bell state measurement, which allowed the polarization state, the quantum bit of the first photon, to be teleported onto the distant photon from the second source. In simpler terms, photon A from source 1 never interacts with photon B from source 2, yet the quantum information moves from A to B. Why is this huge? Because building a quantum internet means you'll need quantum repeaters, nodes that can transfer quantum information across long distances without destroying it. And one of the hardest parts has been matching up photons from different devices. This experiment shows it can be done, a major step toward networks where separate, distant quantum devices can talk to each other. Yes, we are one step closer to truly secure, ultra-fast quantum communication. But, and yes, there's a big but, this wasn't over thousands of kilometers. The two quantum dots were separated by only about 10 meters of fiber. And while the teleportation succeeded with better than classical fidelity, the success rate and distances are still modest. The work now is to scale the distance, boost reliability, and integrate into real-world infrastructure. Still, imagine a world where quantum messages zip between cities, continents, maybe even satellites, unhackable, instantaneous in sense of being teleported. The future of communication is bending reality. Stay tuned. The quantum leap has begun. Subscribe for more deep dives into the quantum frontier.